Good morning, students. In previous class, we completed mass percent or weight percent and mole fraction, molarity and molality. Now we are going to learn about normality. So the fifth one is normality. It is represented by capital N. And definition for normality: the number of gram equivalent weights of the solute present in 1 liter solution is called normality. The number of gram equivalent weights of the solute present in a 1 liter of solution is called normality. Capital N is equal to number of gram equivalent weights of solute divided by volume of solution in 1 liter. So the definition is the number of gram equivalent weights of solute present in 1 liter solution is called normality. And next to the formula. So formula capital N is equal to weight by gram equivalent weight into 1000 by V in ml. So this is the formula. So W2 is the WT weight of solute in grams and V volume of solution in ml, and its units equivalent weight per liter, or the another unit capital N. Capital N means normal. Okay, like molarity capital M or molar, molality small m or molar. Let us solve one problem. Calculate normality of solution containing 4 grams NaOH in 250 ml of water. So NaOH equivalent weight. So what is that formula? The formula is capital N is equal to weight by gram equivalent weight into 1000 by V. So first of all, we have to find out that equivalent weight. Already we discussed that equivalent weight in previous class. So here NaOH equivalent weight. NaOH equivalent weight is equal to molecular weight divided by, so it is a base, so we have to take its acidity. So that NaOH dissociate into Na plus OH minus, so it can give one OH. So acidity of this NaOH is 1, so is equal to 40, so molecular weight 40 divided by acidity 1 is equal to 40. So the gram equivalent weight of NaOH is 40. NaOH equivalent weight is 40. So according to that formula, capital N normality, N is equal to weight by gram equivalent weight. Weight of that NaOH is 4 grams divided by, and gram equivalent weight 40 into 1000 divided by V in ml, V given 250 ml. So if you do this calculation, we will get 0.4 equivalent weight per liter. So N is equal to 0.4 equivalent weight per liter, or N is equal to 0.4 normal. Next to dilution law, Z is equal to normality by molarity, small capital M capital N by capital M. So we can get normality N is equal, this M comes to here. So then capital M into Z. So here Z is equal to number of equivalents of substance. Z is equal to number of equivalents of substance. So normality is equal to molarity into Z. So Z is a number of equivalents of substance. So if there are two substances A and B, two substances are there, react with 1:1 ratio. So these two are react with 1:1 ratio. Then we can write VA is equal to VB if these two are react with 1:1 ratio. Okay, so VA is equal to VB, or we can write with Z VA ZA is equal to VB ZB. So this is the dilution law. Next, sixth one, volume percentage, V by V percentage. So volume percentage, V by V percentage. It is represented by V by V percentage. The volume of solute in ml. The volume of solute in ml present in 100 ml solution. Present in 100 ml solution. The solute present in 100 ml solution is called volume percentage. So we can write that volume percentage of component, volume percent of component means it is solute. The solute volume percentage is equal to volume of solute or component divided by total volume of solution. Total volume of solution into 100. So volume percentage of component or solute is equal to volume of solute divided by total volume of solution into 100. For example, I am taking 10% ethanol solution. 10% ethanol. 10% ethanol solution means 10 ml of ethanol. 10 ml of ethanol present dissolved in ethanol dissolved in 90 ml water. Then the resulting in 100 ml of solution. Then we are getting the 100 ml solution. Means I am taking a one beaker. In that beaker I am taking only 10 ml ethanol. And in another beaker I am taking 90 ml water. 90 ml water. If I combine these two, finally I got 100 ml solution. In that 100 ml solution, 10 ml of ethanol and 90 ml of water. Okay, so 10% ethanol means 10 ml of ethanol dissolved in 90 ml of water. The total solution volume is 100 ml. For example, if I take here 20 ml of ethanol, means 20 ml of ethanol dissolved in 80 ml of water. Finally, I got 100 ml of solution. So 35% V by V solution of ethylene glycol. 35% V by V. Volume by volume. V by V solution of ethylene glycol. ethylene glycol. Ethylene glycol used as a antifreeze in the cars. Antifreeze. In the cars, 35% V by V ethylene glycol used as a antifreeze. Glycol lowers the freezing point of water to 255.4 Kelvin, means minus 17.6 degrees centigrade. Actually, the water freezing point is 0 degrees centigrade. At 0 degrees centigrade, the water is converted into solid. The water is converted into ice. But if you add ethylene glycol to water, the water freezing point decreased to minus 17.6 degrees centigrade. So in some countries, the temperature may be up to 5 degrees centigrade, or up to minus 5 degrees centigrade, or minus 10 degrees centigrade. In that countries, we cannot use the water in cars because the water freeze at 0 degree centigrade, but at minus 5 degree, minus 10 degree centigrade, the water is converted into solid. So we cannot use that water in the cars. So here in such countries, we cannot use that water in your cars because at that countries the temperature is minus 5 degrees, means below 0 degrees centigrade. Below 0 degrees centigrade means the water is converted into solid, means ice. So we cannot use that water in the cars. So if you add that ethylene glycol, how much? 35% V by V ethylene glycol. If you add this ethylene glycol, if you add 35 V by V ethylene glycol into the water, so then the water freezing point decrease up to minus 17.6 degrees centigrade. Means we can use that water in the cars because the freezing point decreases up to minus 17.6 degrees centigrade. So because of that, this 35 V by V ethylene glycol is used as a antifreeze. Next, seventh one, mass by volume percentage. Mass by volume percentage, the mass of solute in grams present in 100 ml of solution. So solute in grams in 100 ml solution in ml is called mass by volume percentage. The mass of solute in grams present in 100 ml of solution is called mass by volume percentage. So mass by volume percentage is equal to mass by volume percentage is equal to mass of solute, the solute in grams, because W by V, solute in grams divided by the volume of solution in ml. Okay, W by V, gram per ml. So gram per ml. So mass of solute in grams and volume of solution in ml into 100. So this is the mass by volume percentage. Mass by volume percentage is equal to mass of solute in grams divided by volume of solution in ml into 100. So it is commonly used in medicine and pharmacy. If it is a medicine eardrop, so if you see on this bottle, so there is a neomycin sulfate 0.5% W by V, mass by volume percentage. Next, methods of expressing concentration. The last one, parts per million, ppm. So parts per million, ppm. The quantity of the solute in grams present in 10 to the power of 6 grams of the solution is called ppm, parts per million. So ppm is equal to number of parts of component divided by total number of parts of all components in solution into 10 to the power of 6. We can take that to parts per million when the solute present in small quantities. And ppm also expressed as mass to mass, and also expressed as volume to volume, and also it is expressed as mass to volume. For example, a liter of seawater, the seawater is liter. Liter seawater weight, WT weight is 1030 grams. Contains 6 into 10 to the power of minus 3 grams. 3 grams dissolved oxygen. And it also expressed as 5.8 grams per 10 to the power of 6 grams. 5.8 grams of dissolved oxygen per 10 to the power of 6 grams. Nothing but 5.8 ppm. 5.8 parts per million. Next one, solubility. So the definition of solubility: the maximum amount of substance dissolved in a specified amount of solvent at a specified temperature is called solubility. For example, if I take one beaker, so in that beaker I am taking the water as a solvent, and I add 1 teaspoon of sugar. 1 teaspoon of sugar can dissolve in the water. So this is the water, and it is a solvent, and here it is a solute. So I add 1 teaspoon solute of sugar in a water solvent. That 1 teaspoon sugar completely dissolved in the water. So then we are getting the sugar solution. If I add 1 more teaspoon of sugar, means in this we have 2 teaspoons of sugar. So that second teaspoon of sugar also dissolved in the water. Means here 1 more teaspoon of sugar also dissolved in that water. And if I take 1 more teaspoon of sugar, means in this we have 3 teaspoons of sugar. If that 1 more teaspoon of sugar not dissolved in that water, so that sugar settle down in the solution. So here the maximum amount of solute is only 2 teaspoons. Only 2 teaspoons of sugar dissolved in that water. So here I am taking, for example, 100 ml water. 100 ml water means ml solvent. So in that 100 ml solvent, only 2 teaspoons of sugar completely dissolved. 1 more teaspoon do not dissolve in that water. Means here the temperature is, for example, room temperature is 30 degrees centigrade. So that beaker at 30 degrees centigrade. And here we are taking the temperature 30 degrees centigrade. So the definition is the maximum amount. So here the maximum amount is only 2 teaspoons. Maximum amount 2 teaspoons. So the definition is the maximum amount of substance dissolved in a specified amount of solvent at a specified temperature is called solubility. The maximum amount of substance dissolved in a specified amount of solvent at a specified temperature is called solubility. So here the maximum amount is only 2 teaspoons. So here what is that maximum amount? So the maximum amount is 2 teaspoons of sugar in 100 ml of water. In 100 ml of water, how much of maximum amount of sugar dissolved? Only 2 teaspoons. So this is the maximum amount of solute. So the definition is the maximum amount of substance dissolved in a specified amount of solvent, specified amount 100 ml, specified amount of solvent at a specified temperature 30 degrees centigrade is called solubility. It's called solubility. So it depends upon the nature of solute and solvent. So it depends upon nature of solute, nature of solute and solvent, and as well as it depends upon the temperature and pressure. And next, solubility of a solid in liquid. So here the every solid does not dissolve in every liquid, and here NaCl and sugar dissolved in water. That NaCl and sugar are dissolved in water. They can dissolve in water, NaCl and sugar. But naphthalene and anthracene. So this is the naphthalene and this one is anthracene. But the naphthalene and anthracene do not dissolve in water. So every solid does not dissolve in every liquid. NaCl and sugar are solids, so solids are dissolved in water, but that naphthalene and anthracene do not dissolve in the water. And here the naphthalene and anthracene dissolve in benzene. That naphthalene and anthracene are dissolved in benzene, but NaCl and sugar are not dissolved in benzene. So every solid does not dissolve in every liquid. So here NaCl sugar dissolve in water, but naphthalene anthracene do not dissolve in water. But naphthalene and anthracene are dissolved in benzene, but NaCl and sugar are not dissolved in benzene. So here we can observe that the polar solute dissolve in polar solvents. Polar solutes dissolve in polar solvents. So NaCl and sugar So these are the polar solutes. That polar solute dissolve in polar solvents. H2O is a polar solvent. So that H2O get poles. We know that Na plus and Cl minus polar, and water, so hydrogen getting partial positive charge and oxygen getting partial negative charge. So polar solutes dissolve in polar solvents, and non-polar solutes dissolve in non-polar solvents. Non-polar solutes dissolve in non-polar solvents like naphthalene and anthracene, non-polar solutes, and benzene, non-polar solvent. So non-polar solutes dissolve in non-polar solvents, and polar solutes dissolve in polar solvents. So if chemical interactions are similar in both solute and solvent, is called like dissolves like. Like dissolves like. Like dissolves like. Chemical interactions. So here NaCl and H2O. The chemical interactions are similar between the NaCl and H2O. And there are similar interactions between the naphthalene and benzene, and there are similar interactions between the anthracene and benzene. So if the chemical interactions are similar in both solute and solvent, is called like dissolves like. Like dissolves like. When a solid solute is added to a solvent, the solid solute added to a solvent, solid solute is added to a solvent, some solute dissolves and concentration of the solution increases. The concentration of the solution, we are getting the solution. When we add solute to the solvent, we are getting the solution. When a solid solute is added to the solvent, some solute dissolves and the concentration of the solution increases. This process is known as dissolution. Dissolution. If I take here 1 teaspoon of sugar solute, I add it to solvent water, then we are getting the solution, sugar solution. If you add 1 more teaspoon of sugar, then the solution concentration increases. So this process is known as dissolution. When a solid solute is added to the solvent, some solute dissolves and the concentration of the solution increases. So this process is known as dissolution. And with increase in concentration, solute particles collide with each other and get separated out of the solution. This process is known as crystallization. This process is known as crystallization. Means here solute added to solvent, then we are getting the solution. With adding of solute to the solvent, the concentration of the solution increases. So this process is known as dissolution. With the increase in concentration, the solute particles collide with each other and get separated out of the solution. This process is known as crystallization. Means here the reverse process. The reverse process is known as crystallization. Crystallization. That solute particles are separated out from the solution with the increasing of concentration. And a solution in which no more solute can be dissolved at the same temperature and pressure is called saturated solution. A solution in which no more solute can be dissolved. No more solute can be dissolved. So here we're taken that if you add 1 teaspoon of sugar in the 100 ml water, that sugar can dissolve in the water. If you take 1 more teaspoon of sugar and that sugar also dissolve in the water, so that is the maximum amount of solute. If you add 1 more teaspoon, means third teaspoon of sugar, that teaspoon of sugar cannot dissolve in the water. So here a solution in which no more solute can be dissolved, so that third teaspoon of sugar cannot be dissolved in the water, so that solution is called saturated solution. So a solution in which no more solute, the third teaspoon of sugar cannot be dissolved in the water. So here a solution in which no more solute can be dissolved at a same temperature and pressure is called saturated solution. So here this is called saturated solution. So no more solute can be dissolved. So that is called saturated solution. Saturated solution. And a solution in which more solute can be dissolved at the same temperature and pressure is called unsaturated solution. Unsaturated solution. Unsaturated solution. Okay. So see here at same temperature and pressure. So here first of all I add 1 teaspoon of sugar. So at that same temperature and pressure, I'm going to add 1 more teaspoon of sugar. So that second teaspoon of sugar also can be dissolved in the water. So here a solution in which more solute can be dissolved at a same temperature and pressure. So that solution is called unsaturated solution. Here if I add 1 more teaspoon of sugar, means third teaspoon of sugar into that water solvent, so that third teaspoon of sugar cannot be dissolved in that of water. Then here that solution is called saturated solution. And a stage when two processes having same rate is called dynamic equilibrium. The dissolution and crystallization, if both are having same rate, is called dynamic equilibrium. So solute plus solvent, so the forward process is dissolution. Here we are getting the solution, and that backward process is called crystallization. If both dissolution and crystallization, if both process having same rate, that stage is called dynamic equilibrium. A stage when two process, dissolution and crystallization, a stage when two process having same rate is called dynamic equilibrium. Dynamic equilibrium. Dynamic equilibrium. And next one, effect of temperature on solubility. The solubility of a solid in liquid is affected by the temperature. So if you consider the dynamic equilibrium, solute plus solvent gives rise to solution. So here the forward process is called dissolution and backward process is called crystallization. So both process are having same rate. So that stage is called dynamic equilibrium. So this is a dynamic equilibrium and it must follow the Le Chatelier principle. Le Chatelier principle. So here, if dissolution process is endothermic, dissolution process is endothermic, means delta H is greater than 0. The solubility increases with increase in temperature. The solubility increases with increase in temperature. With increase in temperature in the dissolution process. This is the dissolution process. The forward process is dissolution process. So in that dissolution process, if the dissolution process is endothermic, means delta H is greater than 0, the solubility increases. Solubility increases with the increasing of temperature. With the increasing of temperature, solubility increases. And if the dissolution process is exothermic, means delta H less than 0, the solubility decreases. Here the solubility decreases with increasing the temperature. With increasing the temperature. If the dissolution process is endothermic, the solubility increases with the increasing the temperature. If the dissolution process is exothermic, the solubility decreases with the increasing of the temperature. And next one, effect of pressure on solubility. So pressure does not have any effect on the solubility of the solids in liquids, because solids and liquids are very less compressible. Solids and liquids are very less compressible than the gases. So pressure does not have any effect on the solubility of the solids in liquids.